All right, I'm Jesse Morgan.
I'm Sarah Faulkner.
Tim Tobias.
For our Fundamentals 3 class, we were asked to design a circuit that can take the relatively low voltage signal of muscle contraction and heart rate and amplify it and filter out any noise to basically create an EKG and display it on a monitor. So, Sarah, do you want to return and go in?
The noise we're mainly trying to filter out is 60 hertz noise. That's just present because that's what voltage at the power outlets runs at. And so we have a filter that has a breakpoint of 500 hertz, and we have it filtering out both a positive and a negative signal. And then we're referencing ground to a bone here, which is my elbow, just assuming that there will be no signals there.
One of the reasons that we chose 500 hertz was because we looked up in medical journals and found that most of the frequencies that we would be sampling was right about that, right in that frequency range. And then after that, most of our sampling and filtering can be done digitally, or we can zero in the EKG to wherever we want. When we're actually doing the sampling, though, that means that we have to sample at about 1,000 hertz in order to avoid any aliasing in our signal, overlap in as far as digitally.
All right, so as you can see here, sampling at an actual sample rate of 1,000 hertz, we get a heart rate signal pretty close to what we expected to see from the project requirements. Then if we decimate and actually start sampling at around 500 hertz, thus negating the Nyquist theorem, we see that we get a little more distortion in between the signals and a much less viable heart rate signal.
There is a lot of noise in the signal, and that can come from tolerances that are actually in the circuit itself, as well as quantized error that comes from actually sampling the data, since we only have so many bits to represent our signal.
Mm-hmm. Okay, can you show what happens as you take the sampling rate lower and lower to the lowest possible rates? So what rate are we at now?
All right, we just step back to 500.
So now we're actually sampling more slowly than our actual signal, and there should be quite a bit of distortion.
Almost like a modified wavelet filter.
Mm-hmm.
Yeah, so it will at 250, so that's half of our.
It's a quarter.
Mm-hmm.
Half of our cutoff.
And what frequency are we at now?
We're now at 125 hertz, an eighth of our normal sampling rate.
Mm-hmm. And what about it? Can you go lower yet?
We're starting to lose information basically, so our waveform looks cleaner, but you can't tell as much from it. It's harder to see where my heartbeat actually is and what's noise.
And it's actually going to skip some samples, and we're going to have less samples per window.
Mm-hmm.
Peaks are much less consistent.
Mm-hmm. And what about your, if you clench your muscles and go for like an EKG or go for an EMG,
Yes,
what
if I
happens?
clench my muscles, we're not going to get a nice pulse, but you'll see a lot of electrical signals from just my muscles being tight.
Mm-hmm.
All right, keep clenching. I'm going to go back to our 1,000 hertz. Show the difference. Still at an eighth, and there's our 1,000.
That's a lot of noise. We learned from Professor Powell that is called baseband wandering.
Okay. All right, and talk a little bit about your board and how you connected it to the myRIO.
Okay, so the board is basically set up for two different outputs. We have the MSP, which is here on the sides, as well as the myRIO. We just have a cable that runs into the myRIO, pretty standard. Everything was routed to the pins that we needed in order to get power and ground to the necessary inputs and outputs. And the way that we differentiate where the power goes is through this jumper right here. Currently it's in the myRIO position, and if we hooked it up to an MSP 430, we'd have to switch over to the next position. Obviously the inputs hooked up to Sarah are over here, and it runs into the IMP, the instrumentation amplifier, and then through its successive filters after that.
Okay. Thanks a bunch. I appreciate